Hello everybody. In this short video, we will be looking at the concepts of electric potential energy, as well as electric potential difference. This is the bedrock for electric circuits because current electricity can only exist provided there is a potential difference. Therefore, I implore you to pay attention. If you have any questions, please ask in the comment section below. I will be more than willing to help you walk you through this concept so that you could actually get it. But first, we need to answer the question, what is electric potential? For me to answer that question, let's assume that we have a charge, positive Q, and we have another charge, small q. Charge 1 is separated from charge 2 by a distance r. What do we expect? We know that like charges repel and unlike charges attract. So what we expect is that 1 will be repelled by 2 and 2 will be repelled by 1. In other words, this is the force that 1 exerts on 2, and this is the force that 2 exerts on 1. By Newton's third law of motion, we know that the force that charge 1 exerts on 2 is equal but opposite to the force that 2 exerts on 1. Now, from Coulomb's law, F12 is equal to 1 over 4 pi epsilon naught q small q r squared r cap. Coulomb's law is an experimental law that quantifies the magnitude and the direction of the electric force experienced by one charge in the presence of another charge. But how is this important in the understanding of the concept of electric potential? By definition, electric potential difference is simply defined as the work done per unit charge to move a charged particle from one point in an electric field to another. So the electric potential difference is just defined as the work done divided by Q. This is the definition of electric potential difference. This means that the work done is equal to Q multiplied by delta V. Another way of putting this, no work can be done in an electric field provided there is a potential difference. In other words, unless a charged particle is moved from one point to another at a different potential, can there be work done in an electric field? Now we are going to explore this concept a little bit further. Now suppose if we have a positive charge and a negative charge, what do we expect? We know that unlike charges attract, so charge 2 will experience an attractive force. This is F12, and charge 1 will experience an attractive force. This is F21. Suppose that we want to move this charge from point A to point B. So we want to move charge Q from point A to point B. How will this be possible? This can only be possible if we apply an external force in this direction. So this is F external. If we apply the force in such a way that the kinetic energy of charge Q remains constant, then we can say that the work done from a to b will be equal to the integral from a to b of f external multiplied by dr. But this is equal to negative the integral from a to b f(1,2) multiplied by dr. This negative sign is here because the electric force is acting to the left and the charge is moving to the right. So the displacement of the charge is totally opposite to the force. And since both are vector quantities, we introduce a negative sign. Now, from Coulomb's law, we know that the force F(1,2) is given by 1 over 4 pi epsilon naught q small q all divided by r squared r cap dr bar. This means that the work done, WAB, will be equal to negative q small q 4 pi epsilon naught the integral from r sub a to r sub b of dr all divided by r squared. This is equal to negative q small q over 4 pi epsilon naught 1 over r from r sub a to r sub b. Recall that the integral of x raised to the power n dx is just xn plus 1 divided by n plus 1 plus c. So the integral of x negative n dx is x negative n plus 1 plus c. So if n is equal to 2, you will have n raised to the power negative 1 minus. That is the origin of this integral. So this will be equal to q small q divided by 4 pi epsilon naught bracket 1 over r sub b minus 1 over r sub a. This is the work done to move the particle from point A to point B. Remember, by definition, the electric potential difference is equal to the work done per unit charge. So this means that the electric potential difference will be equal to Q over 4 pi epsilon naught bracket 1 over Rf minus 1 over Ri. So this right here gives us the expression to calculate the electric potential difference between 2 points, the initial point and the final point in an electric field. It is worthwhile for you to really follow this through because this derivation sometimes can be confusing, especially with a negative sign. Remember that this negative cancel out each other, and that's why you have 1 over Rb minus 1 over Ra. This is the final point and this is the initial point. Now in the next series of in the next few minutes, I'm going to do some examples so that you could actually understand these concepts. So what have we done so far? We know that 1 delta V is equal to the work done divided by delta Q. 2, we know that the work done is the integral from A to B of F dr. And 3, we have proven that delta V is equal to Q over 4 pi epsilon naught 1 over Rf minus 1 over Ri. So this right here gives us the expression for the electric potential difference between 2 points in an electric field. Now remember, electric potential difference is the work done to take a charged particle from one point to another per unit charge in an electric field. Now, in order to measure potential differences, it is important to have a reference point. Now, this is important because electrical potentials really are not that important. What is important and more practical are electrical potential differences. But to measure the electrical potential difference between 2 points in an electric field, one of those points needs to be a point where we are certain of the value of the potential at that particular point. Now, in physics, we take infinity as our reference point, but in practice, we use the ground as our reference point. Whether we are taking infinity or the ground, we know that the potential at infinity is zero. Why is that so? Because if two charges are infinitely very far apart, they do not interact with each other,